Hello everyone. We are here to present our operating systems project titled Energy Efficient CPU Scheduling Algorithm. Our team consists of 3 members, and in this project we focus on designing a CPU scheduling algorithm that reduces energy consumptions while maintaining performance. In traditional CPU scheduling algorithms like FCFS, SJF, and round robin, the main goal is to optimize performance metrics such as waiting time and turnaround time. However, these algorithms do not consider energy consumptions, which is a major issue in the modern systems, especially in mobile devices and embedded systems where battery life is critical. So, the main problem we address is how can we reduce energy consumption without compromising system performance. To solve this problem, we designed a custom scheduling algorithm called Adaptive Energy Aware Scheduler, or AEAS in short form. The key idea behind AEAS is very simple. We run important and short processes at higher speed and less important or long processes at lower speed. This helps us save energy while keeping performance almost the same. Then we use a concept called dynamic voltage and frequency scaling, or DVFS, where we adjust CPU frequency dynamically. So overall AES intelligently balances energy and performance, making it suitable for real world systems. Now my teammate will explain how the algorithm works in details.
Thank you. Now I'll explain how our AEAS algorithm works step by step. So I will open my PPT. First, all processes are stored in ready queue based on their arrival time. At each step, we select processes that have arrived and classify them into three categories: critical process, short process, long process. Critical process, high priority processes. Priority number less than or equal to 2. Lesser the number, greater the priority. Short processes, small burst time less than a threshold. Long processes are background tasks or all remaining tasks. Next, we compute dynamic threshold using the median burst time of the process. This helps us to adapt different workload instead of using fixed value. Then we use schedule processes in following orders: critical first, then short jobs, then finally long jobs. Now come the most important DVFS, dynamic voltage and frequency scaling based execution. We assign CPU frequency as follows: critical process high frequency, short process high or medium frequency, long process low frequency. This ensures that the most important tasks are executed quickly, while less important consumes less energy. We also apply dynamic adjustment. If the process load is high, we reduce the frequency of non-critical tasks. If a process is waiting for too long, we increase its frequency. This prevents performance degradation. We also minimize the context switching by grouping similar processes together. This reduces overhead and improves efficiency. Now let's talk about energy model. Energy is calculated as power multiplied by execution time. We define the power level as high frequency 2 watts, medium 0.8 watts, low 0.3 watts, idle 0.1 watts. High frequency, high performance. Low frequency, lower power consumption. By reducing the frequency for long running process, we significantly reduce the total energy consumption. At the same time, we ensure that the performance matrices like waiting time and turnaround time are not affected significantly. Now I will hand over to my teammate for demonstration and results.
Thank you. Now I will demonstrate our system and present the results. Here we have our dashboard where we can input processes with arrival time, burst time and priority. We also have load preset option with basic with 5 processes, high load with 8 processes, same arrival with 6 processes, mixed priority with 7 processes, single process and staggered arrival. And we will use high load with 8 processes with as an example. After entering the processes, we run the stimulation. The system generates a Gantt chart showing processes execution along with different frequency levels. We also compare our AES algorithm with different traditional algorithms such as first come first serve, shortest job first, round robin, and priority scheduling. Now, looking at the results, our algorithm achieves approximately 36% energy savings, which is a significant improvement. At the same time, performance degradation is kept within acceptable limits, around 5% or less. We also observed that shortage of first give the best performance but doesn't consider energy. AES provides a balance between energy and performance. This makes AES more suitable for real world applications, especially in mobile and embedded systems. Finally, we conclude that AES algorithm successfully reduces energy consumption with maintaining system performance, achieving an optimal balance with efficiency and speed. Thank you for watching our presentation.